Hello everyone, my name is Yatin Gupta and I welcome you all to my channel Double E Concepts. So today we will discuss about the part 8 of Basics of Network Theory, and from today onwards I will start the topic series and parallel combination of resistor, inductor and capacitor. So here we will discuss about how we can calculate the equivalent resistance, inductance and capacitance in a given circuit. Also, we will discuss about the properties of RLC when they're connected in either series or in parallel. And then we'll also discuss about the voltage and current division rule in all these three elements. So in today's lecture, the whole focus will be on the resistor element part only. In the next lecture, I will cover the inductor and the capacitor part. So let's begin today's lecture. Let us first discuss about the series combination of resistance. So the first question comes here is, when do we say that two resistance are connected in series? Let's understand this first. So if I have this one resistance, it has two terminals, terminal A and terminal B. Let's just say I'm saying that terminal A is my start point and terminal B is my end point for this resistance. Okay. Now I'm taking another resistance here and it has two terminals C and D. Now, if I connect them like this, that the end of one resistive element joins the start of the second resistive element like this. So this will be called the series connection of two resistances. Okay. So this is how we say that the resistances are connected in series. So now if I take a circuit like this where n number of resistances are connected in series like this, R1, R2 and so on Rn. So the equivalent resistance of this combination can be calculated as R equivalent equal to R1 plus R2 and so on up to Rn. So in series connection, you just basically add on all the resistance values and you will get the equivalent resistance. And N is here the number of resistances connected in series. Now let me come to the second part of this resistance series resistance combination. Properties of resistance when they're connected in series. Let us discuss about the properties. The same current flows through all the resistance connected in series. Whenever resistance are in series connection, the value of resistance will be same in throughout the branch. So if four resistances are connected like this, and if I'm assuming these are the current values in each resistive element, so if they are in series, it is confirmed that all the current values here will be equal to some one value I. The second property says that the voltage gets divided among all the resistances connected in series proportional to their resistance values. What it says that if I have a circuit like this and a current I is flowing in it, so if I say R1 is the highest resistance and R2 is the lowest resistance in this series, so I can clearly say that the voltage drop on R1 will be the highest one, and on R4 it will be the lowest. So the order will be like this: IR1 is the highest and IR4 is the lowest. So these are the two properties related to series connection of resistance. Now let us move to the next topic, which is the voltage division rule. Whenever the resistance are connected in series, the topic of voltage division comes into picture. Okay, so let us focus on this circuit first. I have some n resistances connected here in series across a supply V, and I is the current flowing in it. So these are the voltage drops across each resistive element, IR1, IR2, and so on, IRN. So how do we calculate these voltage drops whenever a series connection is with us? So for this purpose, we use this formula VR equals to total voltage. Total voltage means uh, the whole series connection. Across this series connection, whatever is the voltage value, that voltage we take here. So this is the total voltage. Multiply it with the resistance value whose voltage drop you want to calculate and divide it with the sum of all the resistances in series like this. So this is going to be V into R divided by R1 plus R2 and so on Rn. So this is an important equation because we are going to use it too many times when we are going to solve problems related to circuit. Okay, so mark this an important one. Now coming to the next part of this lecture, which is the parallel combination of resistance. Till now we were discussing about the series combination. Now let's discuss parallel one. So when do we say that two resistances are connected in parallel? If I take a resistance like this and its two terminals are A and B, and A is the starting point and B is the end point, and now if I take a similar resistance, it has two terminals C and D, and now if I connect them in a manner that the starting point of this resistance, first resistance, meets with the starting point of this second resistance like this, and also the end point as well, we say that the two resistances are connected in parallel. And now if I take some n resistances in the same manner, R1, R2, and so on up to Rn, I can calculate the equivalent value of resistance using this formula. 1 upon R equivalent equals to 1 upon R1 plus 1 upon R2 and so on up to 1 upon Rn, where n is the number of resistance connected in parallel. Okay. Now, the important thing here is you can directly remember for the two resistance in parallel. If you want to calculate the equivalent value of resistance when two resistances are connected in parallel, you don't have to do 1 upon R equivalent equal to 1 upon R1 plus 1 upon R2 and then further solve it and then equate the value of R equivalent. You can directly remember this formula. R equivalent equals to R1 R2 divided by R1 plus R2. So this is an important one. Okay. Now let us move to the properties of resistance connected in parallel. So the first property says that the voltage across all the branches connected in parallel will be equal. If I take this circuit for an example, if the supply voltage is V here, it is confirmed that each branch of resistance that is connected here in parallel with each other, the voltage drop across every branch will be the same. I1 R1 will be equal to I2 R2 and it will be equal to I3 R3 and all these voltage drops will be equal to V only. This is the first property. The second property says the total resistance of parallel combination will always be lesser than the smallest individual resistance value. Like there are n resistances connected in parallel. So whatever will be the lowest resistance connected in this combination, when you are going to calculate the total resistance of this whole combination, it will come out to be less than that smallest individual resistance value. Now the third property says lesser the resistance, higher the current in the branch. So in the same circuit, if I say that R1 is the highest resistance in this circuit, so definitely it will have the highest value of current in it. So lesser the resistance, higher the current. Now, whenever resistances are connected in parallel, current division rule comes into picture. So let's discuss about this also. If I take this circuit for as an example, this is the supply voltage V, total current I is coming here, and it is getting divided like this in the n branches of resistance which are connected in parallel, as you can see. So the value of IR, like the current in any branch which is having the resistance of R, can be calculated with this formula: total current multiplied by the equivalent resistance divided by the sum of resistance in parallel. Now, this will come out as IR equal to I into R equivalent divided by R1 plus R equivalent. This value here R1 is actually R because we are calculating it for R element like R resistance value. Okay, so you can correct this here. This is not R1, this is R here. Now, the important thing here is while calculating the value of R equivalent, we do not consider the resistance whose current we are calculating. What it means? See, when I was calculating for this resistance R1 here, let's just say it's being calculated for R1. In the calculation of R equivalent, I am not going to include this R1 resistance. I will only calculate this whole part as my R equivalent value and not include R1 here. Okay. So let us understand it with this example. Let's just say we have this circuit right here and the total current which is coming out from the supply is zero point 0.3 amperes. Now we want to calculate resistance, the current in coming going into each branch here. So when I'm calculating for this 50 ohms, right? If I want to calculate the current going inside this 50 ohm branch, what I'm going to say that this is my R equivalent value. I'm not including 50 ohm in my R equivalent calculation. 25 ohm is my R equivalent value. So if I calculate I 50 ohms, this is going to be supply current, which is zero point 0.3 multiply by R equivalent value, and equivalent here is 25 ohm only, divided by the total resistance here, which is 50 plus my R equivalent. So 50 plus 25. This will come out as 100 milliamperes. Now, if I want to calculate the current in 25 ohm branch, I'm going to shift my R equivalent from here to here like this. And now the formula becomes I25 equals to zero point 0.3 multiplied by 50. Now 50 is my R equivalent value here and divided by 50 plus 25. And this will come out as 200 milliamperes. So this is how you can calculate the current in each branch when the resistances are connected in parallel format. So that's all for this lecture. In the next lecture, we will discuss about the series parallel combination of inductor and capacitor. Thank you very much.